Thank you everybody for joining us today, and I'm excited to share with you about MSC Apex for the analysis of large fabricated structures. Now, I know many of you on the call have been using Apex for a while. Some of you have just been watching from the outside hoping to jump in, and now's a really good time to do that. And I know some may have actually, this is totally new to you, right? So let's do just a little bit of introduction before we dive into the meat of the presentation. So MSC Software introduced MSC Apex a little bit over 3 years ago, and our vision for Apex is huge. It's quite large, but it's difficult to deliver that complete vision in just 1 or 2 releases, so it takes a little bit of time. And because we can't deliver everything in one release, the initial releases of Apex, okay, were really targeted at some of the biggest issues and biggest problems in computer-aided engineering today. That is the time required to create the finite element model in the first place, the time required to modify it when design changes happen, and honestly just the time required to get an existing model to run, right? Sometimes it's tough to get it to run and to give acceptable and usable results. So the initial releases of Apex, such as Arctic Wolf, Black Marlin, and Cheetah, notice that each release of Apex, if you're new to Apex, each release of Apex gets an Apex predator. We're doing alphabetical predators. So these initial releases really targeted that CAD to mesh pane, and they targeted with some wonderful innovations that were natural and intuitive direct modeling techniques where you directly interact with the model as opposed to working with a lot of buttons and a lot of data boxes on forms. If you had a gap in a surface, you simply drug an edge or a vertex to close the gap. So some of the innovations were this direct modeling, and another innovation was just the idea of automatic model updates from a generative framework that exists within Apex. So as you make changes directly to the geometry or the mesh, everything else automatically updates. So this means that you can make your design changes and get new redesign results much faster with MSC Apex. Now, after the initial releases, some of the later releases of Apex leveraged the integrated solver in Apex, transforming Apex from not just a CAD to mesh tool, but honestly into a structural analysis system with linear statics, normal modes, frequency response, and in fact the most recent release of Apex, which is the Grizzly release, adds new simulation capabilities for linear buckling, and there'll be more to come of that in the near future as well. As a matter of fact, as we continue our Apex journey through the end of this year and into next year, we're going to continue to see Apex grow and blossom into this fully integrated and extensible computer-aided engineering platform with scripting and additional physics capability and honestly much, much more. Today our focus, though, is on the analysis of large fabricated structures like ships or cranes or heavy machinery and things like that. Most of our Apex presentations up to this point have really focused on the productivity that you get in Apex from just building the finite element model faster. And that's true for every model you make, but it's especially true for idealized models, which includes lots of injection molded plastic parts for the mid-surface or even machined bulkheads and things like that require a lot of work to get the mid-surface representation that you want. We're going to shift gears a little bit today, and we're going to look at how all of that comes into play along with the analysis capabilities, linear statics, normal modes, buckling, how all that can apply to help you go not just CAD to mesh faster with Apex, but CAD to results faster with Apex for the analysis of structures such as the ones that are illustrated here. Okay? So if we look at some of the problems that exist today, and not only, honestly, analyzing large fabricated structures, but this could be other structures as well. What we're going to see and what we want to focus on today is how MSC Apex addresses some of the problems that exist in current computer-aided engineering tools, okay? Now, some of those problems are that traditional, and by traditional I mean, kind of like existing or tools that you might have used yesterday or last year or a few years ago. But traditional systems, okay, are honestly, they're very complicated to use, and because of how complicated they are to use, it leads into the second bullet here. It oftentimes takes a long time to build the finite element model, whether the finite element model is highly idealized and complicated for that reason, or whether or not it's not highly idealized. It's just going to take a long time, oftentimes, to build that finite element model because of how complicated these systems are. As a matter of fact, I like to refer to many of them as button farms. They have so many buttons and so many boxes. It's much more intuitive if we can just directly interact with the model, and we're going to see that paradigm, and we're going to see that user experience in MSC Apex. Because the systems are complicated, because it takes a long time, okay, oftentimes people think, well, I got to be an expert to do that, right? And the other thing, and this is really the critical thing, we've surveyed lots of people, and they almost to a person tell us that it takes too long to get analysis results. They do not get the analysis results in a timely fashion. And by timely fashion, that means we can get the product to market sooner, which means we can start making money sooner, right? Or maybe it just simply means we can do more projects, okay? Now we can't do all the projects we want to do because how long this takes. And then the other thing, and this leads into one of the points on the first bullet here, is we often produce suboptimal designs. We don't have time to make it better, okay? We just have time to analyze it the first time and hope that the margins pass. Wouldn't it be nice to be able to analyze it, look at the margins, and then say, what if I can make it better, right? A couple of other problems that we see in many of the existing computer-aided engineering tools today is they're parts and assembly agnostic. They really sort of ignore those, really. And when they get to the simulation part, they flatten that out into a monolithic representation. And what this means is that the time you've invested, and you have invested time in creating this beautiful parts and assembly structure, usually in your CAD system, we're not leveraging that, right? And when we get to the simulation portion, we're absolutely not, because we're analyzing this, once again, this flat monolithic representation of what is a multi-assembly, multi-part structure, right? And what that means is when design changes come into play, and design changes come into play sometimes on purpose. Well, we messed up and we need to do this differently, okay? Or we've got a new requirement now. And sometimes the design changes happen because, well, the margins are too low, right? But the bottom line is this flattening often makes those design changes complicated, expensive, and sometimes result in just a complete do-over, okay? We're just going to start from scratch on this because it's going to be too long to fix what we actually have now, okay? So these are some of the problems. I know there's even other problems. These are some of the things that we're going to focus on today, and we want to look at how MSC Apex helps us address those. So the first thing we want to start out talking about is the user experience that exists in MSC Apex. Because a couple of the first bullets was how complicated and how too long. And the user experience in MSC Apex is natural, it's intuitive, and it's actually easy to learn and easy to use. A lot of this comes to the way we interact with the model. We use a natural and intuitive model interaction, which we call direct modeling, which means if I have a gap between surfaces, I click on an edge and I drag it and I close that gap, right? Nothing is more intuitive or natural than that. Additionally, if I've already got a finite element model that exists here, or I've already got loads and boundary conditions, we have automatic model updates from the generative framework. The database structure of Apex is such that everything's related to everything else, and it knows how it's related, right? So when you make changes, everything else updates automatically, and that's going to save you a lot of time making the model the first time, and a lot of model when you make it again, such as if you need to do a redesign. And then the last thing here in terms of easy to learn and easy to use, one of the difficult tasks often with doing finite element model is just getting the model to run, and if it runs, getting acceptable or usable results. And one of the key features of MSC Apex that will help you out there is something we call analysis readiness, and we'll get to see that live and in person when we do the demonstration later today, okay? So the net result of this innovative user experience that's within MSC Apex, this natural and intuitive direct modeling, etc., is that you're just going to have faster model preparation. And remember, that's one of the things that Apex was focused on initially, was the CAD to mesh problem, how to actually get the model created faster. So in addition to tools like the direct modeling capability, the generative framework for the automatic model updates, we've just got some very innovative tools with mid-surfacing, automatic thickness extraction for solids, mesh quality improvement, We've got tools for solids, tools for shells. We've got tools for beams. We'll see that a little bit later in the presentation as well. So a lot of things that are in Apex that are directly going to benefit you by helping you just make the model faster the first time and faster when you have to do it again. And that always happens. Next is that when you have to do it again, right? Rapid design improvement. And all the elements that are in Apex, once again, this generative framework, which gives you these automatic model updates, this direct modeling, this analysis readiness, once again, they help you the first time, they help you the second time, they help you the third time as well. The net result is I can improve my design faster with MSC Apex. And to date, we've talked a lot when we talk about MSC Apex on the CAD to mesh portion and the productivity gains that you get in just building the model the first time or even updating the model the second time. Today we're going to extend that. We're going to focus specifically on the analysis of these large fabricated structures, and we're going to look at how MSC Apex can help you get results faster, not just generate the model faster, but get usable results faster. Part of that is just building the model faster, but part of that is also the way MSC Apex does the solution. Remember, you've invested a lot in the assembly and subassembly and the part structure of your model, and Apex uses a modern parts-based integrated solution for that. It's more process-centric rather than model-centric. And one of the benefits of this is that you're going to, and we'll see this in the demonstration portion, is you're able to validate your model incrementally on a part-by-part or assembly-by-assembly rather than having to validate the whole model all at once. And many times it's difficult to debug just because of the overwhelming size of everything. Okay? So let's get into a demonstration and let's see how this would work in MSC Apex. So I've got a large fabricated structure. I've got a portion of a large crane structure here, and our focus on this part of the demonstration, and I'm going to do another demonstration after this one, but this focus is to kind of give people, especially people that may have never seen Apex, kind of a feel of what the user environment is within MSC Apex. And we'll look at some of the techniques in the second part of the presentation on how we can really do some of these things really, really fast. Okay, so I've got this large crane structure. It's a large fabricated structure, a lot of metal stock, standard gauge thickness stock pretty much, that's going to be welded together to create this. And one of the things that you can do with Apex, and we've already kind of touted that, is that Apex allows you to keep your rich data structure of your data. You've invested in this, right? So we're going to keep that, and we're going to leverage that in our solution. Now, I've already mentioned I kind of want to highlight in this portion of the presentation some of the features of Apex for people that may not have seen it. And one of the things in terms of learnability and usability is our online help that we have available for this. It's very easy to access some tutorials that help you get started. These are some videos that are available, and to be honest with you, I've worked with a lot of people using MSC Apex. This is how most have learned how to use the product, okay? Additionally, one of the things that I really like, and I've also talked to users who find this really useful, is what I like to call our hover help, where if you hover over a function, it gives you direct access to some videos just on that particular function, okay? This is almost like looking something up on YouTube to kind of know how to do something, fix your faucet or something like that. So it gives you quick and to the point information about the different functions that might be available. Okay, so let's get into working with this particular model now, and I'm just going to look at a subset of it, and we're going to validate this portion of the model before we add it into the entire model. So let's just show only this portion, all right? And this portion that we're looking at is once again very rich in its data structure in terms of parts and assemblies and sub-assemblies and various things like that, all right? So let's come in and let's look at two common problems that I see a lot of times with geometry. And you can sort of see one of those problems already where I've got one of my members that's protruding through another member. This is obviously a mistake, right? I mean, something went wrong here. We like to either blame the the CAD system or blame the designer, and I'll point fingers at myself because I've made this kind of mistake myself many, many times. And this can happen because perhaps you get distracted. You're working on the model, you get distracted, you leave your desk, you forget where you were, and in the end, you overlook this. And many times, because the structure just has so many parts and things like that, you don't even really notice. And the guy that's going to notice is going to be the guy that's got to do the finite element analysis model of this, because this will never do for him. Okay, he's going to want to fix it up. So this kind of represents dirty geometry, all right? So we want to make this piece fit. We don't want it to protrude. We also, if we kind of investigate this piece a little bit more and look at one of his neighbors, okay, what we'll see is that, well, we forgot to put the fillets on this guy as well. So we want to add those fillets. And if we look at one of the other neighbors, we'll see that we've got another neighbor here that's actually got a problem as well. So we've got a couple of problems here we want to address. And we're going to address these with the direct modeling technology that's within MSC Apex. Okay? So let's first look at this guy here. We'll just show him only. And I want to introduce you to some tools that we have for working with the geometry. The first tool is a tool that's designed to work with solids. We call it the push-pull tool. And I want to close this gap. It does exactly what the tool says. I'm just going to grab a face, I can push it, and I can pull it to close up that gap. And that might be something you would want to do in a model like this, because you might not want to have such a fine mesh that would be required to capture that level of detail in your model. Maybe you're actually looking to just do a more loads representation of your model as opposed to a detail representation. Well, the design guy, he forgot these fillets, so in my estimation, and I'll be the analyst in this case, maybe I want to include these, all right, in my analysis. Maybe I think they're important, so I'm going to stick those back in. They were omitted. So this is one of the things that Apex allows you to do. It allows you to clean up geometry that's dirty. It allows you to add things that may have been omitted. So I'll just simply add these fillets in, okay? And we got one more to do. All right, great. So we've got the fillets in. Now I want to come back and I want to tackle the fact that, well, we've got this one piece that's protruding, right? I'm just going to take advantage and I'm going to use this push-pull tool, all right? So I'm just going to say that I want this face of this surface. Let me do an undo here. I want this face on this surface here to push-pull up to this face. Boom, done. All right, so we've cleaned that up. So that looks nice now, all right? Next thing I might want to do is I might want to get rid of these little quarter fillets in here. Maybe those represent a level of detail that I don't want. I can use the push-pull tool on them, okay? Or I can actually use some defeaturing on them as well. So we'll go and use our defeature tool. We can defeature things by just clicking on them and they go away. I know you're probably saying, but Larry, I've got thousands of those. I don't want to click on all of those. Well, we got that covered too, because we can select either an individual part, or we can select the whole model, and Apex will identify the features for us. Okay, I can actually select those features and remove those features very quickly. Once again, whether it's for individual parts or whether or not it's for the entire structure. In this case, I'm going to do an undo. We've got multi-level undo here, so I want to keep that, so I'm going to bring that back. Let's go ahead and create a mid-surface. All right. Because this is a constant thickness section, I'm just going to do a constant thickness mid-surface. All right. Let me bring my surface back so I can see it. Let me hide my solid. We'll bring some mesh up. Let's go ahead and mesh it. And we're going to mesh it with 2-inch elements. Now, this particular structure is actually quite large. It's like 750 inches. I probably would not use a mesh size of this small. I'm going to use it for my purposes today, but we could remove detail if we needed to and have a coarser mesh representation. Or once again, we can keep the detail if we want a finer mesh representation. So there's the mesh. There might be some additional cleanup here. I see some vertices up here. Maybe I'll remove those vertices, and that's going to be the mesh on that part. Let's go do the next part now. All right, so we'll show the next one. And remember, this one had a problem as well. This one just doesn't look like the rest. Maybe this was a design we thought we were going to use, but now we've decided we're not going to use it. And rather than go back to the designer and get him to fix it, me as the analyst, I need to get my work done today, so I'm going to fix it, right? And let's use MSC Apex to do that. So I'm going to go in and create a mid-surface for this one. So rather than repair the solid in this case, I'm going to choose to repair the surface. Let's go ahead and mesh it. I'll use that 2-inch mesh size once again. And what I want to illustrate here is the generative nature of MSC Apex. So I've already meshed this. It's already got a thickness applied. Matter of fact, I can just come up here and show the thickness. It's already got a thickness applied to it. I want to maintain that, and that's part of the generative nature of MSC Apex. So we're going to come in here now, and we'll use the Edge and Vertex Drag tool. I can drag edges if I want to, or I can drag vertices. Notice as I do this that the mesh automatically updates. I can leverage these guidelines to know when I'm square and perpendicular and parallel and all sorts of fun things like that. So we'll just simply quickly make this geometry look like the square that it's supposed to be. I can even do additional things. Maybe I know there's a critical stress area here. So I might want to come in and adjust the mesh seed a little bit. Apex has a very nice feature, kind of like swiping left and swiping right on your smartphone. I can just simply hit the space bar and change a mesh seed if I want to. So I can make that anything I want that to be, and I'll be happy with this particular part. So I've done these two parts now. Let's go in and let's integrate these with the rest of my structure and do a quick analysis on this, right? So let's show everything here for my subassembly. So I will show only my subassembly here. Here's my subassembly. I've got this one piece that I've already created a big surface for. I want to go ahead and mesh that now. So we're going to mesh that, and we're going to use a mesh size of 5 for this portion. So let's mesh all this red stuff there. So we've got a mesh. It's a good idea to go ahead and check the quality. I can see that all the elements are good. I have no invalid elements that would prohibit it from running. And the next thing I need to do now is to assign the thickness for this. So this is just another one-click operation. So I'll just or 2 clicks rather. I'll pick the mesh I want to assign the thickness to. I'll pick the solids to assign it from, and there's a bunch of solids here. And Apex is smart enough to know which solid to extract the appropriate thickness for a given element. It can be constant thickness or it can be variable thickness, and it's even smart enough to figure that out automatically if you want it to be. All right. So we've now got our structure. We've got our finite element mesh on this subassembly. We're getting very close to doing an analysis of it. Now the big red portion here is already connected together. I'm actually using a special connection in MSC Apex called stitching, where I have stitched a bunch of surfaces together. But the two that I just fixed, they're not stitched in. They're not necessarily part of this yet. So I want to make them part of this mesh. I want to connect them in. And I could choose to stitch it, but in this case, I'm going to do something a little bit different, okay? I'm actually going to glue them in. And we've actually got a couple of additional techniques for connecting things together. We're going to explore the edge tie in the next portion of the demonstration. Let's use the glue technique, okay? And the glue technique is wonderful because it's mesh independent. It doesn't matter that the mesh on these little stiffeners here, it doesn't matter that they don't match up, okay? So let's simply drag box everything. Apex says it has glued it. Let's turn the glue on and see it. So I get some positive feedback. The white and the purple here represent the elements that are participating in the glue. So I got some great feedback there. I know that that's okay. Let's do an analysis of this now. I'm going to validate this subassembly of the whole structure, independent of the rest of the structure. And this structure is supported at each end here. So I'm just going to put a fictitious, just a dummy constraint real quick on this surface, okay? And on this surface over here. Let's do that. All right, so I've got that fictitious boundary condition for a second. And I'm going to load it. I'm going to load it with a distributed force. So let's do that. So let's do a distributed force here. It's going to be a force in the negative z direction of 10,000 pounds. And we're going to distribute that force. And let's actually apply that force in this area right here, underneath where the rail would be. So let's pick the surfaces that we want to apply this to. And I'm going to apply it basically in the center. and I'm going to offset it a little bit. I'm going to put it a little bit above. I could type in a dimension. I could exactly locate it if I wanted to, but for my purposes, I'm going to let that be it. So there's my force. So I'm actually ready to run this now, or at least I think I'm ready to run it. Let's find out. I'm going to say place it in the analysis scene, which means to take this section of the model and get it ready for analysis and check and verify and validate it. And this is the analysis readiness that we alluded to earlier. It's going to check my model for things like element quality, connectivity. In this case, it has seen that I have not assigned a material yet. Let's see where I've not assigned a material. And I can see that many of the parts here do not have a material yet. Okay, in this case, at least 3 of the parts. So I will get analysis readiness to immediately take me to the material form so that I can assign that material to this subsection of the model, and I'm now ready to run. I now have a few warnings. I'm going to ignore those at the moment, but I could investigate those further, and let's do our analysis now. This only takes about a minute to run. We'll have some results in just a second, and we'll look and explore those results just a minute. And what I hope you've seen here is just how easy it is to interact with the model in MSC Apex. I hope you've got a feeling that what is a problem in many systems today, which is they're complicated and they take too long to build a model. I hope you can see that in Apex that's absolutely not true. So let's just do a quick animation of our deformation here. All right. I can throw some stresses on it if I want to. Look at some stresses. So we've got some stresses. I could see that my maximum stress is about 3,000 psi, which is actually kind of low. I can see that I can look at my deformations if I want to. We'll go back to stress. And I can actually come in here and throw some hot spots up here. If I want to know where the maximum stresses are located, it'll even tell me which part that is located in. Now these I believe to be fictitious because these were fictitious constraints that I put on this model. So I can actually, if I wanted to, I can add some additional hot spots until I get a hot spot that's maybe in a region that I believe, like this one here, all right? And I, of course, can investigate individual parts if I want to as well. Let's look at, we made this model so quickly, okay? Let's look and see if we can make it better real quick, all right? And the way that I might do that is I might come in here and I might simply say I want to move some stuff around, right? I want to move some stuff around. I want to relocate a part. Maybe that's what I want to do. Or maybe I want to remesh something. That would be another thing that I might do. So let me hide a portion of this mesh so I can see a little bit clearer. And let me come in here and hide a few of these surfaces so I can see a little bit clearer. And for instance, we can see this one part here. Maybe I'm going to redesign this part. So maybe I'll use defeaturing, and I'll come in here and get rid of this little slot. That's gone. Because I've removed that level of detail, maybe I'll even go in and remesh it. Okay, we'll use a larger mesh size. Instead of 2 like we used before, let's use 5. Okay. I know you may be wondering, okay, Larry, you talked about this automatic model update. Am I still connected? I've still got the glue? Yes, I've still got the glue. Let's do one more thing here. So one change was to, update the mesh and remove a detail. Let's just assume, and I think this is a bad idea really, but let's just assume I want to relocate. I want to slide this over, okay? Because I want it to be halfway between these 2 little small stiffeners there. Let's do that. So I'm just going to come in. I'm going to select the guy I want to move. I'm going to select the direction I want to move him, and I was going to say I want to align this edge with the midpoint of this edge. And there's that midpoint. Apex automatically locates things like arc centers and midpoints. So I've relocated that stiffener. I know you may be asking, what about the glue, right? Do you still have glue? Well, let's turn the glue on. I still have glue, all right? So we're ready now to rerun this. All I have to do, Apex is actually telling me that it needs to be rerun, that the model has changed, and I'll just say run simulation, and we're off to the races. We're going to skip now and move ahead because I got some more fun stuff to show you, but we can quickly go in and look at results as well. We'll skip that step at this time. So we've seen how Apex is easy to learn and easy to use. We can see how it's not that complicated because I'm directly interacting with the model. And we've also had a small glimpse of the power in Apex of being able to incrementally validate a small subset of the model at once. And we still keep the big assembly and sub-assembly architecture that you might have. So let's look at how all of that applies to something that's on a larger scale, like a bigger section of maybe a ship model. And let's see how Apex can help shorten the time for CAD to results for something that's bigger, right? So we've got a ship section here we're going to look at. It's got about 4,000 parts in it, and traditionally this section or even larger sections could be a multi-week effort to build and complete. It depends on the level of detail that you're going to keep in the model and you know, what are some of the mesh representations going to be, whether it's beams and shells and things like that. Within Apex, very short, 1 to 2 days to automatically mid-surface it, defeature it, get thickness, connect things together, keep that part and assembly architecture that you have. We want to leverage that in the solution, okay? One of the key things you're going to see in the next portion of the demonstration is how, because we are process-centric, because we retain your assembly and your part architecture that you have, which, by the way, you invested in that. You created that. Let's leverage that now. Apex is going to allow us to divide and conquer. We'll be able to incrementally validate the model, and we'll be able to leverage that in the solution, because when I incrementally validate, let's say this small portion here, Apex is going to keep the stiffness, the mass, the damping matrices that may be calculated and reuse those. So we're going to save a little bit of time when we get ready to run the entire structure. The net, and this is what's important, is CAD to results, right? It's not just about getting the model fast, but it's also about getting usable results fast. And all of that is enabled in Apex because it's easy to use, it's not too complicated, leveraging your parts and assemblies organization that you have for incremental validation, incremental analysis readiness checks on your model. And then when it's all said and done and the solution is done, we've also got some innovative results exploration tools, and we'll even see these things called sensors, which lets us capture specific information at specific portions of the model that may be important to you. So let's take a look and see what this looks like in MSC Apex, okay? So we're done with this one, so I'll close it, and let's go to the second part. So I've got a section of a ship here, and it's a small section, so we can just do this in a very few minutes just to illustrate some of the capabilities. And a lot of the things that I showed previously was the direct modeling and the generative nature. Let's look at how we can do some of those things on steroids now and actually finish this whole model in a very, very short amount of time, okay? So once again, we've got a very rich assembly and sub-assembly structure here that we want to keep. We want to maintain that. And let's look at how we can use the divide and conquer methodology that we can leverage in Apex and leverage your rich organizational structure to validate and get results very quickly. So here we have some frames, okay? Let's look at one of those frames. We'll do this one first, all right? And we're going to incrementally validate this particular frame. This is actually a bunch of solids. So let's first create some mid-surfaces of this, okay? We're going to do constant section mid-surfaces because this is all flat plate stock in this case. So we'll do a drag box and create a bunch of mid-surfaces very rapidly, okay? Let's actually hide the solids so we can see the surfaces, and let's actually automatically color those. I like it when they look different colors, so I can see all the individual parts that I have, and these are the mid-surfaces from those parts. The next thing we want to do is get rid of some of the features that are here. Now, you may want to keep those in your model. That's fine. You'll have to use a much finer mesh size, but for my purposes today, I'm going to remove those, and I want to see how to remove them quickly. We've already seen a little bit of defeaturing in Apex. We can definitely do like the onesie-twosie thing, right? And we also have seen that we can go out and find a bunch of features over an individual part or the whole structure, except those features are standard features like fillets and chamfers and holes. Some of the features that we have in this model don't fit that paradigm. So we've got a special tool here. We call this the Custom Defeature tool. And the Custom Defeature tool allows us to identify a template, and that template represents the kind of feature we want to find. So I want to find that feature. So I've identified that as a template. I'll say Apex, that's a template. It's kind of colored it a magenta color now. I'll now say go look for that on the rest of this thing. It's identified 106 of these. I'll do the middle mouse button, and they're all gone. Okay? Now, one of the key features here are these tolerances, because that template and some of the other features that it found may not match exactly in terms of the length of edges or even some angles. So these tolerances help us move beyond the initial template. Now, I've got a few here that just didn't fit my template, so I'll just do those separately. This time I found 8 that are like that. Those are gone. And then I've got some standard quarters here. I'm going to get rid of those as well. So I'll identify those, and those are gone. So I've gotten rid of a lot of features now. They're all gone in the model. The next thing I want to do is get rid of a lot of extra vertices that I have in the model. These extra vertices would potentially distort the mesh, so let's just remove them. You can see that I've got some vertices on straight edges. I don't need those, but there's obviously some vertices I might want to keep, so this tool is really smart about that, and I can be as retentive as I want to be in terms of keeping or not keeping the vertices, and of course the geometry is not going to change as a result of this, but I should get a better mesh when it's all said and done. Okay, so we'll wait just another second while those vertices are removed, and our next task is to think about how we're going to connect this together. Notice there's gaps between these parts where there's perhaps other members that are intersecting with it, okay? So let's think about how we're going to connect this. And in the previous example, we had some stuff that was stitched, okay? And in the previous example, we used glue. Let's use the edge tie connection here, okay? Now, the glue is great because it's completely mesh independent. The edge tie, it's also mesh independent, but it has a nice little quirk to it where I can start off with a mesh that doesn't match up, but it ensures a congruent mesh. And that's analogous to the type of meshes that most of us on the call are familiar with today. So we'll see how that works. And the first step to doing that is to make sure that all of these surfaces are in a common plane, okay? This is something you would do if you were trying to create a congruent finite element mesh, and because they may have been different thicknesses, they may not be in a common plane. We've got a great tool here for an up to alignment that will align these. So I'm just going to select them all, and I'll say make them all align with this particular face. Okay, it's updated all those. Fantastic. The next thing that I want to do is I want to close these gaps because I want it to be like a congruent finite element mesh, right? So let's close those gaps up here. All right. We have a nice tool for doing that, this Extend Surfaces tool. I'm going to look for some big gaps because I might have some big thicknesses in certain areas, okay? So let's look for some big gaps, and we're just going to say go find them and close them up. If we zoom into this area here, we'll see that that gap is closed. We've brought all those together. I may have actually created an additional vertex or two, so we'll just do a quick add remove vertex and get rid of those. Fantastic. We're now ready to mesh. So let's go in and let's mesh it. I'm going to use a mesh size, in this case, of 4 inches. All right. So let's do a drag box. And let's turn the mesh on so I can see it. And if we go look at it, we can see that it's not congruent here. All right, so it's not congruent. Let's actually do a quick check on quality, make sure that we've got a quality mesh, and we do. But we can see that it's not congruent, and we want it to be congruent, and we want it to be connected in this case, right? So let's go and use our edge tie connection. Let's use a cleanup tolerance of 1/10 of an inch. Let's say we want to connect all of these guys to itself, basically. So Apex goes in and creates, and if we zoom in, we will see that we are congruent. Fantastic. All right. So that's good. Now we're ready to actually incrementally validate. I'm going to introduce a just a temporary fictitious constraint here, so I'm just going to constrain these edges here, and I'll do a quick normal modes analysis. For validation, I could also do a static analysis if I wanted to. I'm just going to find that it's going to be easy to do this real quick. So we created our constraints. Let's say we want to analyze this. We'll place it in the analysis scene. Apex is going to validate and verify our model for us. It says I'm missing loads because it thinks I'm doing a static analysis, so let's tell it normal modes. It also says I'm missing a material, so let's just go in and assign a material very quickly. And now we're ready to actually run this analysis. So we'll do that real quick. And I apologize, I may run a little bit long, so thank you for staying with me. I sometimes find that when I demonstrate and talk at the same time, it takes me a little longer than I actually think it's going to take me, so I apologize about that. So we're just doing a quick normal modes analysis here. Let's look at the results. And once again, these were just some fictitious restraints that I put in just to get rid of spurious rigid body modes, and we can just quickly look. I see a big bending, I see a big torsion. I have validated that my element quality is good. I can build a stiffness matrix, a mass matrix, and everything is connected. So I've verified and I've validated all that. Okay, so let's go and finish this structure up real quick. I'm going to delete those fictitious constraints because those were just in there for that analysis. Let's bring up the other two frames here. All right, and let's continue the process here. Let's go and mesh these guys. All right, I'm going to mesh these with a larger mesh size so the solution time won't take quite as long. So we'll mesh those. Let's assign a thickness to those as well. So I'm going to say I want to assign a thickness to those guys with these solids. Once again, there's many solids here, and Apex is smart enough to know where to go to find which solid to calculate the thickness from. Okay, and I've already done the back panel and these four aft girders. Let's go and do the floor decks real quick. So we'll show those only. Let's hide the solid real quick, and let's mesh this. So we'll create a surface mesh here. I'll use that 11-inch mesh size. Let's assign the thickness real quick. And keep in mind that I could do an incremental solution on this. Oops, got to pick my solids. Keep in mind that I could do an incremental solution on this. In this particular case, in the interest of time, I'm not doing that, but I could actually be running the floor panels. I could be running individual frames just to kind of verify and validate those. So let's look at the structure now. So I've got the rest of the structure, and I'm going to connect everything together. We've just got through illustrating the edge tie. Let's actually glue the rest of this, okay? So I'm going to use a large tolerance here because I've got some plates that are rather thick, and so I've got a few separation distances that are rather large. So we'll just pick everything, and we'll go glue it. And after it's all connected together with the glue, and of course part of the structure is tied together, and I could tie it all together, but it likes to be a little bit quicker to glue it in this particular instance. So we'll calculate, Apex is actually looking to see which parts are close to which parts within this tolerance, and then it's automatically figuring out which pieces need to be connected together via glue. And so it's actually showing me the results of that, which is a little bit busy, so I'm just going to hide that. And let me create some constraints and some loads and boundary conditions. I've actually recorded a macro of that, and we'll look at some scripting in Apex in just a few minutes. So we'll put our loads and boundary conditions on here, and I've just got some pressures on each one of the floor decks here. All right, let's just say, you can imagine I incrementally validated this one web. You can imagine that I incrementally validated the rest. I'm now ready to run the whole thing. Let's put it in the analysis scene. Let's let Apex check the model for me. This is the analysis readiness portion, okay? And it's telling me I've got a couple of problems. Well, one problem is missing material assignment, okay? And Apex will tell you which parts are missing a material. In this case, I've got a lot of parts missing a material. So let's go in and assign material to everything. and you'll notice that that goes away. I've got one other problem here. I've actually got an invalid element. So I've got an element that Apex says would give a fatal error message in the solver. I'll just double click, and Apex is going to take me right to it. Okay, let's hide those boundary condition markers. So Apex analysis readiness has taken me right to the invalid element. Offers me some suggestions on how to fix it if I want to fix it in one of those ways by moving a node. In this case, I can see that the problem is I omitted defeaturing that. So I'm actually just going to go ahead and fix it once and for all. So I'm just going to go in and defeature that. You'll see that that one element gets fixed. That problem goes away. The red exclamation mark goes away. I've got a couple of warnings. I want to do a static analysis, but I've got a couple of warnings. I'm going to ignore those for the minute. Maybe I've got a few elements that could be better quality, but they're not invalid. And I'll just hit the running man here, and so that solution will go. Okay. So while that's running, and it takes about 3 minutes, let's go back to the presentation. And so far, you've seen, some automatic mid-surfacing. You've seen automatic shells. You've seen incremental validation. A few other things that we're just not going to have time to touch on. And I apologize. My Apex came back to the front. Is a few other things that we not going to have time to go into a lot of detail on today is beams. I know many times for a coarser mesh representation of like this ship, is many of the floor beams would be represented with beam elements instead of shell elements. So Apex can do that. You can have a large assembly with a multi-mesh representation. So we got the beam capability there. And one of the interesting features, or one of the neat features about using the beams with Apex is, like everything else in Apex, it is graphical, okay? So I can directly interact with the beams to define offsets and orientations. Up here, we've actually got an animation where we have done the same structure that you're seeing today, and we modeled the floor beams with beam elements, and we actually tied those. We used the edge tie to tie those to the floor panels themselves, okay? So we can do the multi-model representation. I know, once again, this would be done in many cases because we're going to have a coarser mesh representation rather than a shell mesh for every flange and every web of every beam, okay? We also know that we also have capabilities that for solids and for other things. So when you look at your large fabricated structure, you may have a local area, you may have a local bracket that you didn't expect to fail, but it's failing. You want to investigate that. So we can work with solid meshes just like we work with surface meshes, with push-pull and direct modeling. We can do tetrahedral meshes or hexahedral meshes if you so choose. And a unique feature of Apex is the direct modeling works for the hex mesh as well, meaning, as you see in the animation here, I can do push-pull and the hex mesh automatically updates. That's wonderful. We've looked at the edge tie connection, we've looked at the glue connection, and we also saw just very briefly the stitching connection. You may want to have a fastener representation. You may have bolts, and you want to represent those. So Apex supports that. We have a very wonderful way of dealing with that where you simply say, what is the behavior of the fastener? Is it flexible? Is it rigid? Do you want to approximate it as rigid? We'll automatically connect things together, point to point, edge to edge, and we'll extract forces and post-process. We've got some really neat capabilities, and it's all generative, which means that if I update the mesh, the fastener connection updates automatically. So let's go back and see if our solution is done real quick. Let's go back and see if our solution is done. It's just about done, just needs a couple more minutes. It's recovering results now. So we'll have those results in just a second, so we'll just kind of wait while we're here. And the next step will be to look at the possibility of improving the design. So this simulation is completed. Let's look really quickly at the results, okay? Let's look really quickly at the results. And it's a made-up load case, so the results are suspicious, I should say. We've got a maximum stress of around 3,000 psi for this particular loading and constraint set. We can, of course, use our hotspots to identify where those maximum stresses are located. And of course, we can see exactly which part they're located in as well. So if we want to go and do a more detailed investigation. Let's go back now. Let's assume that we've got these results, and let's go back now and let's make a change, okay? Because that's one of the things that Apex is going to easily enable for you, because it was fast to make them all. We're going to get results quickly. If we're going to have time now to go in and explore different design alternatives to know if we're going to have a better design or not. So let's come in, and let's just come into this particular frame here. All right, we'll come into this particular frame, and let's just say that we want to make a copy of it. Okay, in the previous example, we moved one. In this example, we're going to make a copy. So I'll just simply select it all, and I'll just say that I want to make this copy about 50 inches from where we currently are. Okay, so there's my copy. We'll show the rest of the structure here real quick so we can see where this is located in the rest of the structure. So it's very quick, it's very easy to do what if with Apex, whether it's to move a frame if you want to relocate it, or in this example, whether it is to create a frame, okay? Or to create a new frame in a new location, and we've just simply translated this particular one into this new location. So take just another second to move mesh and move everything and get everything located as we wish. And once it's relocated, we're ready to start running the analysis again. Just update, quick update on properties. Because we're actually making some new solids in this case, we'll actually need to recalculate some thicknesses, and then we'll glue this guy in, okay? And we'll be all set. So let's just bring the rest of it up so you can see that we've got this guy located. He is located right here. He's this guy, he's that one. All right, that's our new frame in this particular case. So we'll just show him only in this particular case. I just kept it in this same part. So we'll hide the solid real quickly. And all we have to do, he's already meshed, we'll just update his thickness real quick. And calculate that from this solid. Notice Apex is letting us know we're not quite ready to run yet, which is good because we're changing the model. And it'll let us know. It keeps you updated throughout the process as to when you're going to be ready to run again. So we've actually added that. The only thing we have to do now is to go in and glue that in, and we're ready to do a new analysis. Now, one thing I wanted to show, and I forgot to do as I was talking before, one of the things I know a lot of people like to look at in a large structure is they like to look at like the shear in the moment that's propagating, especially if you're doing a larger loads model. So we have, in the Grizzly release, we've added these cross-section sensors, and I would simply say I want to know the moment at a location in the structure. So I'll just simply pick the portion of the structure that I want to evaluate, and I'll pick the location that I want to put the sensor. I'm going to put it there, and let's actually move him back into there. It initially puts it at the center of the plane, and I could simply locate this anywhere I want in the structure. It can cut through elements or cut through nodes, and I've created for myself a cross-section sensor that will calculate the force in the moment when I redo my analysis. I'm running short of time, so I'm going to go back to my presentation. I apologize about that. So hopefully what you've seen is how easy it would be to update, to go from the original design to adding additional frames or to moving frames. So you saw me add a frame and you saw me update it, and we're actually ready to hit the button and run the analysis. So it was that quick to create and propose a new design. And I'm leveraging all the things that we've talked about, the generative, which is the automatic model updates, the part-centric nature of Apex, which allowed me to operate on that frame. If this had been a monolithic model, it would be difficult to just isolate a frame and move a frame or create new frames from it, okay? In the end, you get a new design with a new set of results. So I hope you see that you do have rapid redesign capabilities for large fabricated structures with MSC Apex. And one other thing I also want to highlight is I imagine that some of you on the call were watching me create these mid-surfaces, extract these thicknesses, and we're thinking, gee, you ought to be able to automate that. And the answer is yes, you can. I didn't automate it because I wanted you to see the steps and I wanted you to experience how easy it was to do. But with MSC Apex Macro Record and Replay that's available in Grizzly, it's very easy to do many of the steps that I showed you today automatically. Here I've actually got a script that's honestly building from scratch a ship section. And I'm actually extracting the data from a Microsoft Excel spreadsheet. I'm able to do that because the macro record replay capability that's available in MSC Apex is actually in Python, which allows me to leverage the rich data structures that are in Python, such as lists and dictionaries, and also leverage the modules that are available, such as interfacing with Microsoft Excel, to use that as an input for the script that I actually want to execute. I know XML is a popular way to input data today. I could have done that. I chose Microsoft Excel because it was a little more visual. You could easily see me making changes to some of the dimensions that are going to be used in this particular instance. So what have we seen today? We have seen MSC Apex applied to the analysis of some large fabricated structures, such as ships or cranes or heavy machinery. And we were doing that, and remember we had 4 problems we were trying to address earlier. The too complicated, the too long, the part and assembly agnostic nature of most computer-aided engineering tools today, and also the inability of many of those tools to get us rapid results the first time, and also rapid results from a redesign. And so I hope what you've seen today is that Apex does enable fast CAD to results for these large fabricated structures. And Apex enables this through the innovative environment, okay, this direct modeling, this generative nature. It's easy to learn and easy to use, okay? And this direct modeling and generative framework enables fast model preparation, and you throw in macros, record and replay, and the Python scripting nature, it can get even faster, okay? The net result is that you get usable results fast, okay? You're able to know they're usable results because you're leveraging your part and assembly structure to do incremental validation, all right? So you know as you go if this is going to give you some valid results when you get to the finish line, which will be the complete structure. All along the way, Apex is checking on you with analysis readiness to let you know if you've forgotten something. And then, of course, once you get the results, we didn't get a chance to dive into it a lot today, but you can also use the innovative results exploration tools that are in Apex to actually explore the results of your design and get the information that you need to make the decision, is this a go or a no-go, right? Net result is that for large fabricated structures, MSC Apex lets you do it faster, do it more reliably, and in a nutshell, you can simply do more with MSC Apex.